Hi there. In this video we're going to talk about geometric series, and we're going to use these to answer a very straightforward question. Suppose I have a bouncy ball, and we're going to drop this ball from a height of 5 meters, and this ball has the property that every bounce it bounces to 2/3 of its previous height. Now the question is, what's the total distance traveled by the ball? Now if you think about this, you should realize that because it bounces to 2/3 of its previous height each bounce, and its previous height is always some finite amount, the subsequent bounce will always be some finite amount. And so we are always adding something, and we'll be adding an infinite number of bounces. Now, in real life, we know that when the ball bounces, it stops bouncing after some period of time. It doesn't bounce forever. So that might give us the intuition that maybe the total distance traveled by the ball is finite, even though we're adding infinitely many things. Now you might say, well, that's because in real life there's a loss of energy. Every time it hits the ground, energy is lost, and so it doesn't match the theoretical picture. In the theoretical picture, certainly if it bounces infinitely often, it must travel an infinite distance. But in real life, we have other factors that come into play. Or is that really the case? Maybe the theoretical picture also predicts a finite distance. Maybe the theoretical picture also predicts that the ball will stop bouncing after some time. So let's go and explore this problem mathematically. Okay, so here we are. Here's the question that we stated. We initially dropped the ball from height 5 meters, and it bounces to 2/3 of its previous height each bounce. So we could draw a picture of this. Right, so that initially it's at 5 meters, and each bounce is 2/3 of the previous bounce. So 2/3 times 5, here's 2/3 times 2/3 times 5, so that's 2/3 squared times 5. We have 2/3 times this, so that's 2/3 cubed times 5, that height. This height will be 2/3 of this, so that's 2/3 to the 4th times 5, etc. So now we have to keep in mind that when it goes down, it also goes back up. So what we can do is we can calculate the total distance by adding up all the distances downwards and then adding to that all the distances upwards, right? So if I look at all the distances downwards, what do I have? I have 5 plus 2/3 times 5 plus 2/3 squared times 5 plus 2/3 cubed times 5 plus 2/3 to the 4th times 5, and this series goes on and on and on. This is the distance downwards. And then we also have the distance upwards. We have 2/3 times 5, and then 2/3 squared times 5, and 2/3 cubed times 5, and 2/3 to the 4th times 5, and again, it goes on and on forever. So we have this infinite number of things to add. Okay, well, we can write these using series notation. This first series, if you look at it, you should see that you can express it in the following way. All right, this is the top series. Notice that when k is 0, we have 2/3 to the 0 power. That's 1. That's 5. That's our first term. When k is 1, we have 5 times 2/3. That's the second term. When k is 2, we have 5 times 2/3 squared. When k is 3, 5 times 2/3 cubed. 4, 5 times 2/3 to the 4th. So we are getting this top series. Now what about the second one? Well, here we have the series k equals 1 to infinity of 5 times 2/3 to the k. So we have to compute the values of these infinite sums to be able to answer our question. So let's start by looking at the value of a finite sum and then extend that idea to get the value of an infinite sum. Okay, so what we're going to do is we're going to look at a finite sum instead of the infinite sum. So we're going to look at this sum. So I'm summing not to infinity, but I'm summing to just some number n. Now, keep in mind, this is exactly what we were looking at. It's some number. In this case, this number a was 5 for us. times some other number raised to the power k. In our case, this was 2/3. 5 times 2/3 to the k, right? And we went to infinity. But I'm just making this more general, considering any possible numbers a and r that you may have here. How would we compute this sum? Well, think about what this is. This is, when I plug in 0 for k, I have a times r to the 0. That's just a. When I plug in 1 for k, I have a times r to the 1. 2 for k gives me ar squared. 3 for k gives me ar cubed. And I'll just keep going until I get to ar to the n. That's as large as k gets. So this is the sum that I'm looking at. And I want to compute what is its value. Is there a nice formula to compute this? Okay, well, let's do a trick here. This is a good trick to know if you're trying to compute the value of something big and complicated. Just say, suppose it's equal to some variable. All right, and we're going to say it's equal to t for total, the total value of this. And I want to find an expression for t. Well, what we're going to do is we're going to multiply t times r. All right, so allow me to do that. R times t, what is that? Well, if I multiply r times t, that's the same thing as multiplying each one of these pieces by r, right? So I'm going to get a times r when I multiply that one, ar squared from this one, ar cubed from this one, ar to the 4th, all the way up to ar to the n plus 1, because I've multiplied by r. So I get this. Now, let's compare this to our original expression for t. How are they different? Well, it's almost the same. You'll notice that these terms, up until I get just before this term, are the same as these. So they only differ by these two terms, right? This expression is the same as that one, minus the a, and adding this. So pause the video now and make sure you can see this, that r times t is equal to this expression, simply by comparing these two lines. Okay, so if we agree with that, let's now take this equation that we have here and solve it for t, because that's what we're after. So what I'm going to do is I'm going to subtract rt from both sides and then move this other stuff to the left. And I get this. Now I'm going to factor out an a on the left and a t on the right. Okay, so dividing both sides by 1 minus r will give me the answer. And this is the expression for t. So let's write this out one final time just so that we can see it as the formula for the sum. This is the formula that we want to keep in mind. A formula for a finite geometric series. But what we needed to do was sum to infinity, not to just some finite number n. Well, let's think about what happens when we let n grow to infinity. Well, let's look at the right-hand side. I have r raised to the n plus 1. Now, if r is a number whose absolute value is less than 1, so it's a number between -1 and 1, and I raise it to a large exponent, what happens? Suppose I take 2/3 and raise it to a very large exponent. Well, I get something very, very small. The larger the exponent gets, the smaller that value gets. So what that tells me is that as I let n go to infinity, this piece right here tends to 0. And so what that tells me is that as I sum, if I were to sum up to an infinite amount, what I would get is a times 1 minus 0 over 1 minus r. And here's the second very important formula. This is how we sum an infinite geometric series, and here is the nice formula. Now, I do have to stipulate that absolute value of r has to be less than 1, and that was needed to go from this step to this step, because we were saying that this piece went to 0 as n goes to infinity. When n gets very large, this needs to go to 0 to get from here to here. If r is a number bigger than 1 or less than -1, and I raise it to a large exponent, it will not get small. So that won't work. This formula only works provided r is less than 1 in absolute value. And this is the formula we need to solve the problem. So here we have returned to our bouncing ball problem. We need to compute this sum. Well, notice that this is a times r to the k, summed from 0 to infinity. We now have a formula for this, and so we know that this is equal to a over 1 minus r. So we just computed the value of this. Now, what about this series over here for the downward parts of the bounce? Well, notice it doesn't quite correspond to the formula because we're not starting at 0 for k. But it's almost the same because this is the same as starting at 0 for k, provided that we subtract off the extra term that we just introduced. Notice, what's the difference between these two series? This one starts when k is 1, right? So the first term is 5 times 2/3. Well, this series has that as well, and so they match from that point onwards. But this one has an extra term. This one has an extra term when k is 0, which is 5 times 2/3 to the 0. Well, that's just equal to 5. So this series has an extra term that this series does not have. So if I just subtract that term off, now they match. I'm going to put parentheses so it's clear that the 5 is not being summed. It's on the outside. 5 is the term in this series that corresponds to the 0. And if you subtract off that term, it's the same as starting at 1. So these are the same. So make sure if you don't see that, pause the video and think about it. Convince yourself that these two things are the same. But now that we see that they are the same, we have a formula for this, same formula we used for that one. So let's apply that formula. And we can simplify everything now. 1 minus 2/3 is 1/3. 5 divided by 1/3 is 15. 15 plus 15 minus 5 is 25. And the units that we're using here are meters. And so we have answered our question. The ball will bounce a total of 25 meters. Now, that's cool, right? It is true. We have proved that it is true that even though it has an infinite number of bounces, it bounces a finite distance. Even though we're adding up an infinite number of numbers, we're getting a finite quantity. Pretty amazing, right? And you might say, well, you know, in real life, this theoretical model wouldn't exactly describe what's happening, right? However, it's no less amazing because, yes, in real life, there's going to be a little bit of energy loss. Maybe the ball will hit a pebble every once in a while. It won't bounce exactly 2/3 every time. It may stop earlier than that, but it will definitely bounce no more than this. So even in the theoretical picture, even if it were to bounce an infinite number of times, we have proved that in that case, it will still bounce a finite distance. And so that fact alone, I don't know about you, but I think that's pretty amazing. That even if we were able to succeed in moving this thing an infinite number of times, it would still necessarily only travel a finite distance. So we talked about two very important formulas, and I just want to put them up on the screen here just to remind you of what they were, because they're worth writing down and remembering. We have the formula for the finite sum of a geometric series, and we have the formula for an infinite sum of a geometric series. And keep in mind that on this infinite sum, we have to make sure that the r, the common ratio, is in less than 1 in absolute value. Otherwise, that formula does not apply. But in the case that it is, we have this nice, tidy formula to help us sum an infinite geometric series.